Hello everyone, welcome back. So this is our last class, and the first topic we're going to tackle is researcher degrees of freedom. And there's a really great article about this, false positive psychology, that hopefully you've already read. It's up on Blackboard. So let's jump right in. So what are researcher degrees of freedoms? Well, they're the many choices researchers make, especially the undocumented ones, when deciding how to collect, process, and analyze data. So if you think about our statistical degrees of freedom, often the number of participants, that is one factor that determines the power of our test. The researcher degrees of freedom are a little bit different. They're the choices we make when analyzing our data and presenting our data. And some examples, well, there's many examples, but we're going to look at four, specifically the ones that the article covered. So it's choosing among dependent variables, choosing sample size, using covariates, and reporting subsets of experimental conditions. Now, why are these important? Well, what we'll see is that you can, by making certain decisions that may or may not be transparent in the manuscript, you can drastically affect your false positive rate, or your alpha, or your type 1 error. Those are all synonymous with each other. And typically, with our statistics, we do a lot of work to control alpha to be 0.05. Now, sometimes it's not 0.05, depending on the post hoc test, things like that. But we try to stay honest with about a 5% chance of a false positive. That is a conclusion where we say, yes, there is a significant difference when in reality there is not. So we want to limit the number of false positives that we make. Our researcher degrees of freedoms also affect our alpha. So let's take a look at that. First off, though, I think this is from our very first class, maybe the second one, where we talked about the types of mistakes we can make. And we have good situations. That's a true negative. So the stats say, oh, there's no significant difference. And in reality, in the population, there's no significant difference. So that's good. That's a true negative. Then we have a true positive. That's also a good result. So the green ones are good. And that's when we say, yes, there is a significant difference. And in reality, there is a significant difference. So that's also good. So what we're really talking about today is a false positive. And this is represented by alpha. So we typically set alpha to 0.05. And that means there's a 5% chance that we're going to make a type 1 error. Or we reject a true null hypothesis. So we're saying, yes, there's a significant difference, when in reality there is not a significant difference. The other mistake we can make is a false negative, and this is represented by beta, and that we typically look at power, which is 1 minus beta. But we're not so much going to worry about that. That one's definitely gets more complicated, but today we'll focus on false positives. So with our researcher degrees of freedom, there's lots of choices we make when analyzing data. Many of these we end up describing in our manuscript, but some we don't. And that is not necessarily to be misleading. That's kind of just how manuscripts are currently written. But we'll see at the end here some suggestions on how we should change our manuscripts to be more forthcoming about our researcher degrees of freedom. Now that alpha with researcher degrees of freedom can get so high that it's possible that most research findings are false. There's this famous article that suggests that, based on all the researcher degrees of freedom, that more often than not, we're probably reporting false positive results. This is a very interesting article if you'd like to seek it out. It's a little more technical than the current one, but it's also an interesting read. All right, so let's delve into these four different examples. There are other sorts of examples, but the most common ones are captured in these four. They're the ones the articles looked at, and they're the ones that are probably easier to actually put some data behind to try to understand. So first off, choosing among dependent variables. And in this, they presented a pretty simple experiment where you're measuring, you have some sort of manipulation. So imagine you've got two groups, control group and experimental group. And this could be a within or between study. It applies in either case. And let's say in both those groups you measure two things. you measure liking and willingness to pay. So I think these are more psychology researchers, so those variables may be more interest to them than say to us. Now they had to make an assumption here that these two variables had a strong correlation between them of 0.5. The results we'll see do change depending on the correlation, but they kind of set it right in the middle to look at the most moderate case of this relationship. So when you report these results, you might choose to report both. Maybe both of the variables ended up being interesting, so you report both. But maybe only liking was interesting and willingness was not significant, so maybe you don't even report it at all. Or it could be the other way around. Willingness was really interesting, so you're going to write your manuscript on that, and you don't bother reporting liking at all. So you have some researcher degrees of freedom here, which variables to report. And you can imagine this is a simplified case where we have two dependent variables. We'll look later when you may have far more than this. So the statistic here that we're looking at is, do the two groups differ in liking? We could also look at, do the two groups differ in willingness to pay? Or do the two groups differ in a combination of liking and willingness to pay? So those are researcher degrees of freedom there, a choice on how to report our dependent variables. So with a bunch of simulation, what they showed is when you have this decision about which one to report, that affects your alpha. Because you can kind of bias your findings. Well, if one isn't significant, well, we'll report the other. And if it's the other way around, or maybe they're both significant. That flexibility in which you choose to report affects your alpha. And instead of having a typical alpha of 5%, it could be inflated to as high as almost 10%. And when you read the article, if you've left out one condition entirely, let's say you've left out liking, you don't even mention that you measured it, a reader would have no way of knowing that you collected that and that your alpha, because of your researcher degrees of freedom, is not 5% like the statistics suggest. It's actually twice as high. Now that's actually a pretty simple situation where you have two dependent variables. And I decided to kind of pick on myself here for an article that I published with Dr. Harry, where it's somewhat of a typical biomechanics study in that we have many, many dependent variables. And I think in a lot of our research, we have many degrees of freedom, many dependent variables, but biomechanics is definitely maybe a little more to the extreme. So the research I do, yes, lots of dependent variables. Whenever I get involved in some biomechanics, it's maybe even a few more. So in this example, this article, you can see here, table 1, let's see, we have landing height, landing time, loading time, attenuation time, loading rate, and peak vertical ground reaction force. So that's 6 dependent variables. Our manipulation, our control, and our experimental is an internal focus, external focus. And we've also broken that down into how males and females respond. So we're also looking for a sex difference, and we'll come back to that a little bit later when we're talking about covariance. So already 6 dependent variables. Are those all of our dependent variables? No. So if we go to our next table, I think there's another 16 here. Yeah, so we're up to 20. So this is a lot, right? Are these all of our dependent variables? No, they're actually not. If we look at table 3, we have another 8. So I've lost track now. That's 20-something dependent variables. What is our effective alpha here? Well, it's not 5%. It's not 10%. It's going to be a lot higher. How high? I'm not sure, because it's difficult to calculate, and within that article they use a lot of simulation to determine that. So I just wanted to show you that 2 dependent variables and a 10% alpha, it actually could be a lot higher in lots of realistic studies that are out there. Okay, next example, choosing your sample size. So how many participants are you going to collect? Now in a perfect world, the sample size would be determined by a power analysis. So before you do your study, a priori, you would say, well, this is we need to collect 48 participants for 95% power. That is typically hard to do, to run a perfect power analysis. It's kind of imprecise, not the math, but the information. Often you don't know the effect size in the population. So a lot of times we're left kind of guessing how many participants to collect, and there's definitely a big factor of convenience here too. So yeah, it'd be great if every study I did I collected 1,000 participants, but that would slow the pace of science, to a crawl. Sometimes you have to do that, but other times we want to collect as few participants as possible. There's also some ethical concerns here. So if your study puts participants at risk, even a slight amount of risk, then you wouldn't want to have to collect more participants than necessary. You don't want to expose more people to that risk than need be. Some of this research we do in kinesiology has very little risk. If you think about coming into my lab, pressing some buttons, that's just like working at a desk. That's very, very low risk. But you can think of medical studies, maybe where people are exposed to radiation or a new type of treatment that could have side effects. In that case, you really don't want to expose more people than necessary. Okay, so back to sample size. So often what we do is we decide, okay, well, I want to collect so many participants. In this first case I've highlighted here, in this case, the researcher said, I'm going to collect 20 participants, and then once I get 20, I'm going to test whether my results are significant. Then what they're going to do, and this is where we get into some of the problems with the researcher degrees of freedom, is they're going to say, okay, well, if they're not significant, I'll test more participants. And in this case, the gray line means that they're going to test another 20. So they'll test 20. The results are not significant. Let's pretend. They're going to test another 20, and then they'll check, are the results significant? And let's say they repeat that, and they're going to repeat that over and over until the results are significant. So because of that repeated testing, which is something you might not include in your manuscript, which would be definitely misleading your audience. If your audience just sees, oh, they collected 60 people, they assume you run the statistic once. No, we actually collected 20, ran statistics, collected 20, ran statistics, collected 20, ran statistics again. So 3 times, for example. That changes your alpha as well. Instead of it being your typical 5%, it's much higher. It's about 10%. And this can get worse depending on how many participants you collect between testing and how often you test. So in this example here, this researcher collects 10 participants, checks for significance, and then we'll keep testing 10 more. So they'll do 10, test, 20, test, 30, test. That means their effective alpha is actually more like 14%. And let's go to the very worst possibility here, or the one with the highest alpha. Here, the participant initially collected 10 participants, and then they're going to collect one more. I think I mixed up my axes on some of these other examples. But here, so the black line means you initially collect 10, and down here on our x-axis, this is how many do we collect again before running statistics. So imagine you collect 10, run statistics. Oh, not significant, let's collect one more. So 11 now total. Run statistics. Not significant, one more, 12. Run statistics. So we're running statistics a lot, and that is biasing our alpha. And if in your manuscript you just say, oh yeah, we collected 26 participants and ran statistics, that's misleading your audience. You actually collected 10 and kept repeating your statistics every participant. Now let's think about that worst case here, where you collect 10, run statistics, and then keep running them after every single participant. What you could find is a spurious false positive. So here's, this is one example from the article where they look at the p-value at 10 or 11 participants. I'm not exactly sure where this data point is. And they say, oh, it's not significant. Okay, one more person, not significant, one more, not significant, one more. Keep going, and then, hey, if we get down here to maybe 24, 25 participants, your results are significant. So the researcher who's being a bit manipulative doing this would then say, okay, well, I'm going to stop because I have a significant result. But that could just be a bit of a spurious finding. And in reality, if they collected some more data, and maybe this is, they have a more appropriate level of power here, So they're finding the actual result is that these groups are not significantly different. So if you use this to repeatedly test, you might just be pulling out that single time where maybe you had a strong outlier or you get some sort of spurious result and you say, oh, that's great, let's stop there, let's run with it. Now your p-values aren't necessarily always going to look like this, and I looked at some of my own data as a counterexample. So in this study I had a fairly good number of participants, ended up with 41, and we were looking at, for this variable specifically, the difference in reaction time when you move with vision and when you move without vision. And I won't bore you with the theory behind this, but when you have vision, your reaction time is a lot shorter. When you don't have vision, your reaction time is a lot longer, because you prepare a better movement off the bat because you know you're not going to have vision to help correct your movement as you go. So there's a big difference, fairly large effect size. This wasn't the primary variable of interest, but this was just one variable that we expected based on a lot of previous literature to have a fairly large effect size. So if we look, we ran stats after 41 participants, and we got, there's a very small p-value here, very close to 0. So we said, yep, there's a significant difference in reaction time with and without vision. What I did afterwards is, okay, well, let's try running this stat like they did in that article, after 10, then 11, and 12, and so on. And what you can see early on, likely from a lack of power, we don't have enough participants for this comparison, is that they're not significantly different. The p-values change. They go up, they go down. Participant 15 might have showed a bit of a different trend, so the p-value goes up a bunch here, but then the overall trend is that it does get smaller and smaller. So if we were being manipulative in our reporting and running stats every single participant after 10, maybe we would have stopped at maybe 17 or 18 participants as soon as we saw significance. But that can lead, definitely increases your alpha and can lead to these spurious, significantly positive results where the p-value, like in this previous example, was only temporarily significant, and it's probably because your test was underpowered. All right, next example. So using covariance. I don't do a lot of this in my research. I have done a little bit of research with sex differences, which is a covariate, and that's maybe the most common one, at least that I could think of. Analyzing your data by sex or gender. And if we go back to that biomechanics study that I was an author on, I showed you earlier, we did look at the difference between males and females. So we looked for a sex difference. So this table, they again ran some possible scenarios for what may happen if you use a covariate. And their example, they also looked at controlling for gender or an interaction with gender with treatment. So it's kind of like the situation where we had two dependent variables. Do we pick one? Do we pick the other? Do we use both? Well, if you think of your data, you could look at your data collapsed across gender. You could look at gender separately, or you could look at the interaction with gender. So you kind of have three choices in this scenario. So very similar to before when we had two dependent variables, three choices on how to report them. Here, when we look at, are we going to use gender, are we not going to use gender, or it could be sex instead, that is going to increase your alpha. That's another researcher degree of freedom. And instead of it being 5%, as the stats suggest, it's more like 12%. And the problem here often comes that in your article, whichever result works out the best, you would be tempted to only report that one. And then people would think, oh, well, they haven't tried every single possibility and abused their researcher degrees of freedom. This is what they planned in advance, when in this case it wasn't. We're working our researcher degrees of freedom, kind of fishing for a positive result. Another example of having choice is you could report subsets of your experimental conditions. So again, they have a very simple example in the article about having three different groups. And here I've just made up some groups to go with this. So let's say we have a control group, they take no caffeine, and then we have two experimental groups. One takes the Rockstar, I don't know if it's X-Durance or Cross-Durance, 300 milligrams of caffeine. And then we have the Eternal Energy 10-hour shot group. They take this shot of caffeine, which has 422 milligrams of caffeine. I saw these on Caffeine Insider website, and the Rockstar Endurance they described as having an extreme amount of caffeine, which sounded more like marketing than anything else. But the 10-hour energy shot they labeled as having a dangerous amount of caffeine. Okay, so let's say we collect those three groups, but when we look at the results, maybe we decide that, oh yeah, you know what, it was really only interesting when we compare control to the 10-hour shot. So we're gonna drop Rockstar group, and we won't even report that we collected it. So again, this is another researcher degree of freedom. Or maybe the control and the Rockstar group was the most interesting, so we won't even mention that we collected data on this 10-hour G-shot. Or maybe all three groups are interesting, so we're going to report all three. Or maybe the only significant result was between Rockstar and the 10-hour shot. So there's more flexibility here for the researcher, a researcher degree of freedom, in what they report. And that would be, again, misleading your reader. If you collected these through three groups, you should report that you collected those three groups. If you decide in your data to focus on maybe two of them, the reader should be clear to the reader, and the results for all three groups should be included somewhere. If nothing else, maybe in an appendix to your paper. So back to the table from the paper. So looking at this condition where you might drop a group, you might not drop a group, you're going to use your researcher degrees of freedom. Your alpha could be much higher than 5%, could be around 13%. So here we have the full table. And what I want to draw your attention to now are these bottom situations where you don't just do one of these things, you do a combination of them. And the most extreme case, of course, would be if you do all four of them simultaneously, A, B, C, and D. And so let's say you have multiple dependent variables, you are manipulative with your stats, you record you test 10 participants, and then you keep testing one and keep running statistics. You've got gender involved, maybe you drop a condition that you collected. Well, your alpha is not 5%, it's much, much higher. It could be 61%. And in more realistic studies that we run, where there's maybe more than one covariate, maybe there's more than 3 experimental groups, maybe there's more than 2 dependent variables, this effective alpha wouldn't be 61%, it could be even higher. And this is where we get to that article that says, well, most research findings are false, because if you can imagine, in a typical article with several dependent variables, maybe more than one covariate, maybe your alpha is 80%. And then it would be true that most, or more than 50% of research findings would be false. So this is a very serious issue. Thankfully, the authors don't just bring up this issue, but they suggest some solutions. And all of them kind of come down to being transparent with your researcher degrees of freedom. So the ultimate solution, if you will, would be to only do a pre-registered study. So pre-registered studies, basically you submit your intro and your method, and you say, this is what we're going to do. This is the number of participants. These are the exact statistical tests that we're going to make. You eliminate any possibility to do something different after the fact. You're eliminating your researcher degrees of freedom. And that's a great approach. And some types of medical science, you have to do a pre-registered study. They're not that common yet in other areas of science, like in kinesiology. Also, the authors do bring up that after we collect our data, there is sometimes a need for exploration. Often in our experiments, we may have one strong hypothesis beforehand, but then we also want to explore the data and see what else happens. So we can't necessarily always know in advance everything we're going to do. So we need to have some flexibility in how we analyze our data. But the key here is to be transparent about when things were set out in advance, and when you explored your data later, you need to be transparent about that so people can understand the effect that that has on your alpha. So their first requirement for authors here is that they must decide the rule for terminating data collection before data collection begins and report this rule in the article. So this is going to prevent someone from, say, collecting 10 participants, collecting one more running stats, collecting one more running stats. I guess you could still do that, and if you wrote that in your article that you did that, it would probably be rejected. The reviewers would say, well, you can't do that. So if you set your rule first and then follow it, that would be best. So your rule could be, hey, we did a power analysis, and turns out we need 20 participants, that's what we're going to collect. That would probably be the best case scenario. But you might also report that, hey, we're doing something similar to this other study. They had 20 participants, so we're going to do 20. Or maybe we'll do a little bit better. We'll have 30. Or maybe it's a practicality issue. Maybe you'll say, hey, this was for a thesis project, and we had 2 semesters to collect data. We tried to get as much data as we could in 2 semesters. And that would be fine. So next up, they suggest that authors should collect at least 20 observations per cell. So if you're doing a between group comparison with 2 groups, you should have 20 participants in each group. And the reason they suggest 20 is because with less than 20 participants, to find something significant, it's probably going to have a large, or maybe even more likely a very large effect size. And often what we study doesn't have a large effect size because those things are easy to see, and they've probably, in well-established fields of research, they've probably already been described or discovered. Often we're looking for mediums, effects with small and medium effect sizes. And for medium effect sizes, 20 participants per cell is definitely a minimum. For small, you're probably going to need even more than that. So they're saying you should have at least 20, and if it's less than that, you should really justify why that's appropriate with, for example, a power analysis. 3 and 4 here really come down to eliminating possible researcher degrees of freedom. So you must list all variables that were collected in a study. So if you're reading a study and they're reporting one variable, but then they say, oh, we actually collected 100, this is the only one that was significant, you might view those results a little differently. Likewise, authors should report all experimental conditions, even failed manipulations. And I think that's fine. If you say, hey, we had 4 groups, 2 of them weren't significantly than control, we're going to focus on the most extreme group, the one that took that 10-hour energy shot. The reviewers might ask you also to include the results from those failed groups in an appendix, but at least now it's transparent what you did in your study. Number 5, if observations are eliminated, authors must also report what the statistical results are if those results are included. This is also to get away from another research degree of freedom where maybe you only get a significant result if you remove these 2 participants. So you need to be clear about that. You need to say, hey, we eliminated these participants. You should say why. And then maybe in an appendix, if it's not that interesting, say what do the results look like with or without those participants. I often see this in reaction time studies when researchers have decided to exclude reaction times, maybe ones that are too fast, like less than 100 milliseconds, or maybe ones that are really slow. So that's pretty typical in research on reaction time, to eliminate very fast and very slow reaction times. But the results typically say, hey, this is what we found, and then there's often a statement that says the results were not different even if those outliers were included. Or maybe they were different, and then they should report how those were different. Then the reader or the reviewer can determine, well, are they manipulating their researcher degrees of freedom? Is this some sort of spurious finding that they only get when they get rid of slow reaction times and they get rid of these two participants, or does this seem to be appropriate what they've done? And similarly to number 5, if there's a covariate, then you should report the results with and without a covariate. So I hope you found it interesting, this look at false positive psychology, or looking at researcher degrees of freedom. And I think this is something we definitely all do in our research. After we collect data, we're often curious, what do the results say? But we just need to be careful about how we explore our results, and more importantly, how we report the process that we took. We need to be transparent in everything we did. We don't want to mislead the reader and just present this perfect story in the end where we get rid of all these things, and the reason the story is perfect is because we have abused our researcher degrees of freedom. We need to be transparent about the process that we took, so that we don't abuse our researcher degrees of freedom, and we don't report these findings that are really only significant because our alpha has become huge from our manipulations. All right. Next up, we're going to talk about 2 more topics. Capstone is last, and the next one is our writing styles. So I'll see you in that video shortly.